Thank you, Jim. Thank you, Jim. We're going to talk a little bit today about corrosion and stray current mitigation. It's mostly going to be stray current mitigation. There's just a little bit of corrosion in the beginning of it. Let's see what I'll do a little survey. What kind of engineers we got in here? How many civil engineers do we have? Okay, structural. Wow, not as many structural as I thought. Electrical. Good bit of electrical. Okay, that's mostly what corrosion is: civil, structural, and electrical. We get into some other stuff. I mean, we got the architects in the room. Okay. Well, I'm usually a real pain in the neck to an architect, but yeah, they have a purpose too. Okay, so what do I touch here? Just the arrow button?
Space bar or the down arrow, either way.
Okay. Okay, just quick. What is corrosion? It's a reaction of a metal with its environment. Okay. We're going to be talking about DC corrosion. There is a phenomenon such as induced AC corrosion, but we're not going to talk about that today. That's a whole different subject we could talk a week about. There's a lot of different forms of corrosion. We're going to talk about these two today: galvanic corrosion and stray current corrosion. There's, like you say, there's a lot of other different kinds, but I don't have enough time to talk about those. We're going to go through a lot of slides. I got 88 slides here we got to get through, so this is going to be kind of quick. Okay, why does corrosion occur? It's law. We have laws of physics. First two laws of physics tell you why corrosion occurs. You can't destroy or create energy. You can only change its form. And the entropy of an isolated system is going to increase. Okay, we take iron oxide. We add a lot of energy to it to get this steel. Corrosion brings it back to the iron oxide. So it's physics is what causes it. And then there's a couple of graphics kind of showing it. You know, gold is pretty much stable in its ore form. You find gold in the ground, it's yellow, it doesn't change much. To get magnesium, you got to do quite a bit of refining to get magnesium into a metal. And when it corrodes, it goes back to its ore. Just another thing. Gold and water doesn't do anything. You set it there, it's not going to react. Again, it's pretty stable. Sodium metal, if you ever seen the science experiments back in high school, they drop a little piece of sodium metal, it'll actually spontaneously combust. It'll buzz around and it'll actually light itself on fire. It takes a lot of energy to make sodium into a metal. This is what it takes to cause corrosion. You got to have an anode, a cathode, an electrolyte, which is a conductive medium, and a metallic path. Okay? This is a quick little demonstration. Look, corrosion in action right there. Most of what we're going to talk about here shortly is galvanic corrosion, which corrosion occurs when you have two different metals that are in contact with each other. That's the basic of galvanic corrosion. There's a definition there, but that's basically what it is. You got two separate metals that have different energy levels. If you contact them, they're going to try to come to an equilibrium, and that's what will cause corrosion of one of the other two. They've made up a practical galvanic series, which again, you see magnesium up here. It takes a lot of energy to make magnesium metal, and it's on the anodic side. It has more energy. Graphite doesn't take much. It's almost naturally occurring, coal. So it doesn't take much. It's on the cathodic end. If you connect magnesium to graphite, the magnesium will corrode and protect the graphite. And the spacing between the metals in this list kind of gives you an idea how strong the corrosion cell is going to be. This is what it looks like in real life. You got a steel pipe, you got a brass valve. There's a little bit of moisture in the threads. The steel corrodes, and the brass is the cathode. Same thing here. You got a brass valve and a steel pipe. You get moisture in the fittings, and you're going to have corrosion. This is a pretty classic one. We've got a ductile iron pipe. It's got a brass corporation stop and a copper service line there. Copper is pretty cathodic. I mean, it doesn't take a whole lot of energy to make copper. And this is going to have an anodic area right on here where it's going to eat out the threads basically, or around ductile iron, and you will get leaks. Not all corrosion is bad. Corrosion can be good. It lights our light bulbs, our flashlights. A DC battery is a corrosion cell. The corrosion current, when current travels through something, it creates work. Basic physics, flow of current creates work. It can create good work or bad work. It can create really nice work too. And without corrosion, we wouldn't have gone to the moon. We're not going to go to Mars without corrosion. It takes batteries to go there. Okay. So corrosion can be good. It's not always bad. Okay, how do we stop it, the bad corrosion? How do we mitigate that? Okay, we have these elements of our corrosion cell. We take away any one of those and the corrosion will stop. We no longer have an electrical circuit to allow corrosion to happen. How can we do that? Well, we avoid putting these metals together in contact with each other. We can use insulation between the different metals. We can use coatings to reduce the amount of that surface exposed to the electrolyte. Or we can apply cathodic protection. And the next little slide is going to kind of show you cathodic protection in action. You saw our original corrosion cell where we had a cathode and an anode, and this corroded to protect that. Well, what we can do with cathodic protection is take another more active metal that's got more energy than either one of these, and it'll protect them both. We don't really stop corrosion. We make the corrosion happen where we want to. We manage corrosion. Okay? So we take the corrosion and we put it here where we want it to happen. We can monitor it. We can measure it. We can protect both of these here. Excuse me. That's kind of what it looks like out in the field. You got a ductile iron pipe. This is a chunk of magnesium inside a cloth sack that has bentonite clay in it and a couple of little scavenger chemicals in it, like sodium sulfate. And this is the magnesium. You saw it was like 1.75 volts. This is the ductile iron, which is about 0.5 volts. So you got about 1.25 volts or so of voltage here to drive the current. Okay. If you don't have enough voltage, we can do what's called impressed current. Basically, we put a battery in series with our circuit and drive the voltage. You can make this is a step-down transformer right here. You can take 120, 240 volt, three-phase voltage, step it down to get DC output. It runs it through a set of diodes and resistors. And you can regulate the voltage to whatever you want to drive as much current as you want. You kind of change the anodes, but it's another way of doing it.
When you do that, you keep it as a sinusoid, or is it a flat level, approximately a flat level DC?
For this?
Yeah.
It depends on a single phase rectifier is going to have some AC ripple in it. You're going to get 2 pulses for every AC. If it's 3-phase, you get 6 pulses, so you get a smoother one. What we're going to talk about in a minute, straight current, the DC they use on a transit system is actually a 6-phase, so you get 12 pulses, so it's even smoother DC. And you can put chokes and filters and stuff that help smooth it out some, but there is some AC ripple in those. I think for a single phase, the DC ripples is somewhere around 40%. We're going to talk mostly about straight current because that's a lot of what I do. I do a little bit of everything, but straight current is one of the things I do mostly. And it's one of the things that probably you guys may not be too familiar with. It's got a very simple definition. It's current flowing in an unintended path, straying from its path. Why does it occur? Well, you got to have voltage to drive a current, so it occurs to potential difference at 2 points in the earth. The amount of current that's going to flow depends on the resistance of the paths. Okay, the amount of voltage and the resistance of the path. Electrical engineers know about parallel current theory, so parallel resistance theory, excuse me. The current will divide based on the resistance of the multiple paths. Okay. A structure that's positive with respect to the surrounding earth is going to discharge current into the earth. It's positive with earth, like that magnesium anode. It's driving the current to the pipeline. structure that's negative with respect to earth is going to pick up current. Okay? And soil resistivity, that's the resistance of the soil, and that's going to regulate how much current can flow through that circuit, because that's a resistor that current's got to flow through. Okay, DC traction straight current, like what we have here in Atlanta, the MARTA system, like light rail systems in other cities. The intended path is for the traction power current to go through, in this case, a third rail, which is another rail lane next to the tracks, through the train, and the train's just like a light bulb. It runs, does work, makes the train move, and then returns on the rails. Okay, that train's just like lighting up a light bulb. Stray currents occur whenever part of that current off those rails, the rails, they use just like a big old wire to return the current. Well, that's not infinite resistance to earth, so some of that current's going to get into the earth and leak and be a parallel path. So that's really what stray current is. This is what it looks like. My PowerPoint skills. And so the current's returning, it comes down the third rail, makes the train move, and it returns. Okay, where it gets right here, this rail is going to be positive with respect to earth. It's trying to drive the current. Current flows from plus to minus. So part of that current can leak to the ground here, and eventually it has an equilibrium point here, and then goes negative. So it'll come back. The current's going to complete its path, so whatever leaks off's got to get back. When you got a whole bunch of trains running around, that simple little graph that looked like this, you got multiple trains all over the place. This is what voltage in a single spot looks like. That's dynamic stray current. Okay? That's the voltage that causes a stray current. It's not really the current. That's the voltage that causes a stray current. In this case, that's 50 volts. That's plus or minus 50 volts. Okay? It is a bipolar current because, like you saw, that point depends on where the load is, on where this positive or negative. As that train moves, that graph goes like this. So it just starts, when you get a whole bunch of trains, it's all over the place. But it's pretty uniform plus and minus, like it's plus 50 volts, minus 50 volts. For an ungrounded system, there's different kinds of systems.
So is that a current at a specific point in the system? Or is that
This is a voltage at a specific point in the system.
and what kind of current is that?
Well, it depends. We'll get to that.
What magnitude?
What's that?
What magnitude current will it be?
Well, for a traction power substation, the amount of current that's traveling those rails and returning to the substation is somewhere in the neighborhood of, well, it depends on the system, but it can be anywhere from like 6,000 to 8,000 volts or amps.
Well, I'm thinking about the diameter of this stray current. So what 50 volts, what current level would that be a personnel data?
Well, we'll get to that. We'll get to that. Okay. This just kind of shows where if it leaks off, if there's another conductor in the ground, in the soil, where this current's wanting to flow in the soil, a pipeline is a better conductor than soil. So part of that current's going to get on the pipeline, travel until it gets it's going to be, this is positive, this is going to be negative, and it gets positive here, and it's going to come back to the rails. Corrosion is going to happen where the current leaves the pipe. It's actually going to get a little protection where it goes onto the pipe.
If the train uses the motor to slow down, does that reverse the process?
No. There is a thing they call regenerative braking that'll feed current back into the system, but it actually puts more current onto the rails. But how do you know if you have it? We just kind of saw that. You know, it's current that varies either in the path, amplitude, or direction. Typically, you see a fluctuation. If you have a pipeline and you're measuring the voltage on your pipeline, this is what it's going to look like on a pipeline. You saw on the transit system, the rail voltage is a lot. It's like plus minus 50 volts, sometimes 70 or 80 volts. On a pipeline, you see we're talking plus to minus a couple of volts here. So that's kind of a relationship between what the voltage is driving the stray current and how much stray current can get on an alternate conductor. Okay, and whether this is too much or not enough, it kind of depends on the system. This one looks like it's not seeing really anything. It's not moving it around. It's got a little bit of fluctuation, but it's not moving it. This one's got a little bit more, but it's still within what we would call a criteria for protection. These are two protected pipelines that are around a transit system. You're going to see some activity. Whether it's bad and has to be mitigated is a question on what your voltage levels are. Okay, why do we care? You know, it's kind of a characteristic of a transit system. Well, where street current leaves the rail, where current leaves something and goes into the ground, it causes corrosion. So it eats the rail. It eats the bottom of the rails, you know, where it's got contact and it's discharging. So that's a pretty good motivator for a transit system to keep stray current to a minimum, because it wears out their rails and the fasteners and the reinforcing steel and everything around it. Okay. It also it can cause damage to other things around, like the pipelines and bridges and things. And we'll get into more of that. But this is a pretty astounding number. And this is from about, gosh, that was at least 5 or 6 years ago, the study they did that came up with that. Each one of you guys right now is about $1,100 for every man, woman, and child due to corrosion. Now, it's a study, and they lump a lot of things into what they say is corrosion damage, but it's still a big number. You know, it's bigger than what most people would realize. So it's an important thing. Another reason why we care is because of Mr. Faraday. He tells us how much metal is going to get eaten up by amount of current. Okay? 1 amp of current will consume approximately 20 pounds of steel in a year. That's a lot of steel. Okay? This is an example I used to show to the pipeline companies, or vice versa. When I was working for a pipeline company, I'd show it to the transit agency to say, this is why we care. You got a 12-inch pipe with a 3/8-inch thick steel. If it's discharging 1 amp of current, 2 days, it's going to have a hole in it. You got to respond quickly if you got a serious stray current problem. Okay, that's a pretty severe one, but it can happen, and it has happened. That's what it looks like. What we got here is stray current was moving this way down the pipe. It hit the resistance of this joint here and jumped through the soil to this and kept on going to its source. Where it jumps off the pipe to get around this joint, that's where your corrosion occurs. Same thing here. I can tell the current was going this direction to try to get back to its source because of where the corrosion is. This is pre-stressed concrete cylinder pipe. I don't know how many folks deal with that on a regular basis. That is a nightmare in a stray current area. Okay, it's a great material out not in stray current areas. If you're not in chlorides and you don't have stray currents, it's a great material. But it's a poor application for stray current areas because it's sensitive to both the pickup area and the discharge area. These pre-stressing wires, if you get too much voltage on them, it can hydrogen and brittle those wires. So it can snap the wires from picking up current. It can snap them from corroding where it discharges the current. So it's a real sensitive material to stray currents. Steel and concrete. The steel's a conductor. We have a lot of reinforced concrete structures around the transit system. If we don't manage the stray current properly, we can have accelerated corrosion of the reinforcing steel and spall concrete all over the place. Okay, so we're going to get into how we, at a transit system, try to design to minimize and manage the stray current. That's really where we're going to spend some time here. The approach is to control at the source. We don't want stray currents getting out. Like I said, it corrodes the bottom of the rails. It affects our structures first, so it's in our best interest to minimize it. Okay, and how do we do that? We minimize the driving voltage, which we saw at that one graph where it's all over the place. We try to minimize that, and we maximize the resistance to earth. There's a lot of words here, but okay. This kind of gets to your point, Roger. The maximum running rail to earth voltage coincides with the minimum OCS or contact rail running voltage. This is where the electrical engineers get in here. They do modeling studies to find out where's the lowest voltage, because it takes a certain amount of voltage to drive the current to make the train move. Okay, that's typically somewhere between 525 and 535 volts. So they design their positive system to make sure they keep at least that much voltage between the substations. Okay, where they have that minimum voltage, that's where the maximum voltage on the rail is. Okay, and it takes a 750 volt system, there's 1500 volt systems too. But maximum voltage is 900 volts to run those trains, and then they have voltage drop across the positive that gets to this 535. So there's a couple of different criteria they model. One, they got to make sure they have at least that much voltage between their power substations, and they can't get over, typically criteria is 50 volts nominal, and then if they have one traction power substation drop out of service or for maintenance or whatever, they go up to 70 or 90 volts. Okay, that's the two criteria they model to. All right? And usually you're going to get about a mile to a mile and a half between traction power substations to get that number. All right? This 50 volts is the driving voltage that pushes a stray current into the ground. So we want that to be as small as we can. On light rail systems, that's generally around 35 volts is about what they run at. Heavy rail systems are more in the 50 to 70 volt range. This is what a traction power substation looks like. This is a big one. This is like what they have at the MARTA system and other heavy rail systems. They usually have 2 rectifiers in there. They're like 3 megawatts apiece. A pretty good amount of power. This is a modular one. This is what they use on light rail systems mostly. Some of them will have 2 rectifiers in there. A lot of them have 1. They're just portable. You set them in there and they're prefab almost. Takes a lot less power to run a light rail than does a heavy rail system. Okay, so how do we minimize voltage? How am I doing on time? We want to make the resistance to that return rail, or that return system, as low as we can. You know, current times resistance equals voltage. We got to have the amount of current to run the train, so we got to minimize the resistance of that return circuit so we can manage our voltage in that return circuit.
That's your clock. That's how long.
Okay, so we're halfway done?
Third of the way.
Okay. Okay, so that's how we manage the rail voltage. We got a certain amount of current that's going to be in those rails. We got to minimize the resistance of that. We do that through making sure we use continuously welded rails. We try to minimize the amount of mechanical joints we have, bolted joints. We bond the rails together where we can. Some signaling sometimes makes that difficult. And then we have track-to-track cross bonding, so we try to get as many of those rails in our return circuits as we can, so we have a lot of parallel resistances, so it lowers the overall resistance of our return circuit. This is kind of what it looks like. This is welding a rail. This is one way of welding a rail. This is an exothermic weld. It's a chemical reaction that causes a weld. It's cool. That's what it looks like when they put the mold on it. This is like what it looks like when they fire it off. It's pretty impressive if you've ever seen one. I wish I had the video of it. You'd see. I mean, you want to back away. You see, you aren't standing too close to it when it goes off. And when they're all said and done, this is what it looks like after they clean it up. That's how they do continuously welded rail. You can also do, you know, like the electrical arc welding as well. Yes, it is. There's been some studies where they're concerned about cracking around the welds from the heat affected zone and things like that. So some people are getting away from the exothermic welds and going with the electric welding. This is some rail-to-rail bonding. This is what they call an impedance bond. There's a couple of insulated joints in the rail right here. They use insulated joints to break up the signal circuits, so they know where the trains are. They have what they call signal blocks. Well, we still got to get the traction power around those insulated joints. So what they do is they put in what's called an impedance bond here, and that'll block the signal, but allows the current to flow, the traction power current. This is a mechanical joint. You see this in a lot of the crossovers and what they call special track work. We put bonds around those because this is not a very reliable low resistance connection right here. This is what it looks like when setting it up to do it. It's as much for stray current controls because that current's going to get through this, enough of it to run it. It might reduce the efficiency of it a little bit, but what that'll do is if this wasn't bonded here, this could create a pretty high voltage across this joint and cause corrosion to that joint where the current's arcing across there and jumping across there and stuff. It's as much for stray current control as it is for traction power current. Okay, maximizing the resistance surface. We talked about how we manage the voltage on the rails. Now we talk about how we raise the resistance as much as we can so the current doesn't get through the resistance. To do that, the electrical engineers are going to have a fit here. We use an ungrounded system. How many of you guys have ever designed an ungrounded system? Okay, it's kind of uncommon though. So that's how we do it. We have an ungrounded distribution power system. We isolate the positive, the contact rail, or on light rail system you see the wires overhead. That's insulated from ground. And then the tracks, we put insulated fittings on them and everything to keep them isolated from ground. That's how we maximize the resistance to ground to try to keep that current on that positive and negative and not leak into the soil. And we also separate the traction power systems for what they call a shop, which is where they do work on the trains. That's all grounded because that's a personnel safety issue. You don't want to have any kind of potential difference where a guy's grabbing a train that's energized and can touch a grounded surface. So that's all well grounded. Sure.
Distinction between one specific rail traction power and ranging rails that are grounded, de-energized.
I'm not sure I understood the question. Can you say it again?
And clearly, which point are you referring to an energized rail, so we traction power, versus other rails that are grounded?
Okay, inside the shop, those are grounded. We put insulated joints on each side of the shop to electrically isolate that from the rest of the track because we don't want the rest of the track grounded. But that piece we want grounded because of the personnel safety. Okay?
Rails on the system are not where the trains run.
Right. Let me get to the next slide and we can see it a little better. This is a typical yard. Okay, this is the shop right here. This is where they do work on the trains. They got a lot of tracks coming here. Right off this, what they call the apron, we put a sets of insulated joints right in here, right in here. And this is all grounded tracks in there. The amount of power they use inside a shop is very low. So there's not a stray current problem. We do a lot of bonding around it to contain any stray currents. We also put insulators at what they call yard leads here at these turnouts where it comes off the main line and goes into the yard. There's another one right here. Because, again, parallel resistance there. You got a lot of parallel tracks in here, so the overall resistance of that, even though individual tracks are high, parallel resistance is pretty low. And again, this has like a 5 or 10 mile an hour speed limit in here, so it's not real high. They're not trains accelerating, so it's a pretty low load. But we want to keep that, that's all right. We want to keep that separate from the main line, which has all the train activity and everything on it. So we separate that. It's called segregation. That helps us to maintain the resistance. Okay. The electrical isolate track from ground, we put insulated fittings on it, or we put an insulated pad under it. Or if it's embedded, like in a streetcar or something like that, we put an insulated boot around it to try to isolate it from ground. And we talk about isolating the positive as well there. Okay. There's different kinds of tracks. This is called direct fixation track. You got a concrete plinth here. It's kind of hard to see, but this right here is a rubber encased pad that you set the rail on, so it isolates the rail from ground. This is tie and ballast track. Those little white things you see there, those are insulated pads that for the what they call a rail clip that holds the rail down. It insulates the rail from the clip, and there's a little pad underneath the rail as well. Another thing about this, we're supposed to keep an inch clearance between the bottom of the rail and the rocks to help keep it from touching the ground. This is embedded track. We put a rubber boot around it. This is actually developed up in Canada at TTC up in Toronto Transit Commission. They developed it for noise and vibration. We just got lucky that it's also a pretty good insulator when they use rubber. But you can see just by the design of it, the gap between this rail and ground is only right there and right in here. And guess what? Those fill up with dirt and junk a lot. So embedded track is the lowest resistance type of track we have. This is what the boot looks like when they're putting it on out in the field. It comes on a big reel and they put it around the track and usually tape it on. This is what they call green track. It's a special kind of embedded track. I hate this. It's pretty. The architects like it, but from a stray current standpoint, that's the worst kind of track you can have. Okay, but the architects like it. Actually, in Europe, they have some fake grass that they have developed that makes it look like grass, only it's porous and drains out. This is typical embedded track. You see, this is actually part of the streetcar system in Atlanta after they constructed it. It's all concrete. You can't see too well, but there's the boot around that. And we got to put drainage on the tracks. We don't want the sheet flows, covering it up, because if this fills with water, that creates a conductive path for the stray currents. So on direct fixation and embedded track, we put track drains every once in a while. We make sure that it drains the water as best we can.
Leaf, sticks, front.
Yeah. And that's one of my pet peeves. They don't maintain these once they install them. You got to maintain it. You see grass growing out of these things, they haven't maintained it. And it's not uncommon to see grass growing out of these things. And they got to blow these out every once in a while too. The flange way there where the wheel goes.
Are there supporting ties underneath the grass?
Yes, there is. Next thing we do is anything that's touching the rails, we either have to have it isolated from ground or isolated from the rails, because we don't want a direct connection to the power neutral ground. This is a switch. This is there's an insulator there, there's an insulator there, there's an insulator there, there's an insulator there, one there, one there. And these two things are insulators as well. There's a lot of insulated parts on a switch, and switches move, so it's a maintenance nightmare, because over time things that move that are insulated tend to break down. This is a typical light rail system. This is what it looks like on a drawing of paper. We insulate it. It's called double insulated. You insulate it from the pole and you insulate it from the arms here. This is what it looks like in real life. You got your two insulators here. You got a little insulator right there, and then you got an insulator up there. So it's double insulated. So if one fails, it's got a secondary insulator there. That also helps with any kind of lightning flashes and stuff too. This is a common third rail type system. This is either porcelain or fiberglass. It's an insulator. It's setting up off the ground a good 6 inches. What is it, 6 or 8 inches? Something like that. Those are pretty rugged. It's pretty rare for the positive to leak because it's very high resistance. I mean, a tracked earth resistance is somewhere in the neighborhood of 500 ohms per 1,000 track feet. A contact rail or an overhead contact system is more like 40 mega ohms, kind of, from relative terms. Okay, so we talked about how we try to minimize, control it at the source. Okay, we try to minimize the voltage, maximize the resistance. You're always going to have some stray current coming off a transit system because it's not a perfect insulator. So you got to, all right, what are we going to do about it? How do we manage and mitigate what we know is going to happen? We try to minimize it so it's very little, but we still need to design some safety around it. And guess what? The first thing we design safety for is our own stuff. Okay? Best thing to do is if you can use non-metallic materials, do it. They don't conduct, you don't have stray current problem, bye-bye. Okay? Next thing we do electrical continuity bonding and selective electrical isolation. There's a lot in that little sentence. And then we can use some cathodic protection systems for like the pipelines and stuff to help mitigate some of the stray current. And last case, for if we got too much stray current, we can put in what we call a mitigation bond and reverse current switches, but we try to avoid that because that's a designed ground to our system. We design a ground to our system, we increase the stray current to everything else, so it's a kind of a domino effect, so we try to avoid that if we can. Okay, reinforced concrete structures, that's one of the main things I have to deal with. There's lots of different kinds of them around there. We have the track slabs, which you saw like the direct fixation track, and then we had the embedded track, okay? We got retaining walls, some of them are precast, some of them are cast in place, some of them are soldier pile and lagging. There's a lot of different ways to build a retaining wall. I like the modular brick ones myself because they go away from me. It's not a good conductor. Yeah, very little if any. We got bridges and viaducts. We got all different kinds of those. You guys love to design all different kinds of bridges. It's like artwork. Well, artwork causes me problems sometimes. And we have tunnels, and there's a lot of different ways to build tunnels. And then we got the passenger stations, and there's a lot of different ways to build passenger stations. We got to account for that. That's one of the things that keeps me busy is I got to wait until a lot of this stuff's designed to put my stuff on top of it and say what we need to do about stray current, because it changes based on the different types of structures. But in general, what we're going to do is any reinforcing steel that's parallel to the tracks, we want that to be electrically continuous. Now, structural engineers and civil engineers, where the lap splices are, we like those welded. That means you got to use A706 rebar, not the A615. All right, that changes your steel densities. You know, those laps, when we weld the laps, that changes some of your calculations. So the structural and civil engineers that do that rebar stuff don't like me sometimes. But I try to let them know ahead of time, as close up front as I can, that this is what we're going to be doing, so they can work with it. Every once in a while, we put what we call a collector bar is. We put a transverse one across the longitudinal ones to basically equalize the current flow on the longitudinal ones. And then we put test stations in every once in a while so we can test it and monitor it. This is kind of what it looks like. You were asking about, is there ties underneath the track in that embedded track? You got these cross ties here, and then you got your reinforcing underneath it. This is one type. All that longitudinal reinforcing is going to be electrically bonded, so it's a designed parallel conductor that will maintain, if there's stray current, that's the first thing it's going to hit. We design it to give it a conductor that we can monitor and maintain, and it prevents stray current get out from around that and getting on. If there's a water line right here, it would help to prevent, it minimize the amount of light, current getting on that water line, because we're catching it ourselves in our structure. This is a retaining wall before concrete. In this case, these rebars going this way, we would want to have electrically continuous. Then every once in a while you add an extra bar in here to, again, distribute the current. And also in the footing we'll put those. And wherever you got expansion joints or where there's no continuity, we got to put bonds across it. And then we put test stations at the ends and in the middle and every once in a while. Bridge and viaducts, okay? We kind of work from top of rail down. Where can we isolate? And then whatever we can't isolate, we got to do the continuity. If you can isolate the superstructure from the substructure, that's great. If you got elastomeric bearings and we can have the superstructure separate, that's great. And then it's like, all right, well, where in the superstructure can I work with? If you can't isolate that, then we got to put bonding on the substructure and bond everything. It gets to be more expensive and more a headache. The abutments, we do the back wall, the vertical bars, so current gets onto it, it gives it a place to go. And for ballasted decks, this is something we've been starting to do, is put an elastomeric waterproofing membrane on there that is also dielectric, has dielectric properties, so it's basically a shield. And then we'll put like a welded wire fabric type mesh underneath it to make a current collector to keep it all away from the structure. I mean,
How do you keep the membrane from getting scratched or chipped when
it's really tough stuff. They use it on freight rails a lot. Well, you got to have an inspector out there watching it too. You know, and a lot of times they'll put protection board on top of it. Even though the manufacturer says you don't need protection board, they'll put the asphalt protection board on there. It's basically asphalted 1/4-inch plywood to help protect it. Inspection's a big deal on all this stuff. Tunnels, it depends on what kind of tunnel it is. Basically what the inverts, where they pour the tracks in the tunnel, it's the concrete in the bottom of the tunnel. If it's a circular tunnel, we'd bond the rebar in that longitudinally. And part of the whole purpose of why we do that is when we bond all the longitudinal rebar, if that current gets on there and it gets going on and off, because there's trains going all the time, there's going to be places where it's coming on and going off. The amount of current coming off of an individual rebar is very low, so the corrosion rate of that would be very low, and instead of concentrating it. If we didn't have it continuous, it would be jumping like on those pipelines where it jumped across the joint, where you have resistance in those rebar laps. You would have a little corrosion there and it would end up popping at those laps. So that's why we weld those and we make it continuous. It gives it a big surface area for that current to transfer. And then we can also monitor it. And then whether or not you do any bonding of the tunnel structure itself, it depends on the construction of the tunnel. If it's a segmental tunnels where they got the little panels they put together, generally we won't have to do anything to that. We actually tell them not to bond anything there. We keep it as electrically separate as we can, and we just do the track invert. Passenger stations, again, this is where the architects get involved. So there's a bunch of different kinds of stations, you know, and they can make them pretty, and they slab on grade, we typically bond that. Slab on a grade beam, we typically bond the grade beam. Elevated stations, if we can actually get a separation between the track structure and the station structure, that helps us out because now it's electrically separated. Underground stations, those you got to kind of take a look at how they build them. A lot of stuff that a corrosion guy will say is it depends, and that's true because we have to deal with a lot of different other disciplines, and we have to kind of respond to what they have and how they decide to build things. And sometimes we got a little bit of influence how they decide how to build things. Sometimes we don't. This is a big one right here. For stations especially, we got to coordinate everything with the grounding plan because you got electrical safety grounding for the commercial electrical there. We don't want to have what we bond as rebars, you know, for our straight current to be tied into the electrical grounding, because if we do get straight current on that, now it can transfer to the electrical grounding and get out all over the place. We try to contain it as best we can. Okay, underground utilities. This is always an estimator's nightmare. It gets always underestimated in the project as far as the amount of time and money it takes to deal with the utilities. Just ask the streetcar people if there's any in here. Any transit system, they always, I haven't been on one yet they haven't underestimated. You see different ways of doing this, but they have what basically called a utility exclusion zone or a utility free zone. They've got a certain distance underneath the tracks that they don't want anything there. This is a civil structural thing. You know, you can kind of tell by the way this is drawn that there's a load, and they don't want any utilities within that load profile. I'm not a structural engineer, but I know that much about it. There's different ways of drawing it. You can have it like this. You know, it can be square, it can be angular. But basically what it is, they don't want anything right next to it. They don't want anything right underneath it. If you go down here, you can do it. If you go out here, you can do it. But they want to, there's two reasons for that. One is so they can maintain the utility without disturbing the tracks or the transit system. The other is just the load factors from the, you know, the structural loads. Okay, we're getting there. Okay, there's a lot of different ways we can do it. Basically, you're going to lower the pipeline underneath the track. There's a lot of replacements. If you can do that with non-metallic, do it non-metallic. That makes everything go away, okay? If it's got to be metallic, we're going to make it electrically continuous, and we want it to go at 90 degrees, because if you got current wanting to go this way, you put something this way on it, it doesn't want to jump off and use that as a conductor. So we don't want angles, you know, real acute angles, I don't know. You don't want a high degree angle, because then it's almost parallel and it can use that as a conductor. So if it's going this way, we cross and then go that way. We don't take it across. And then we'll put insulators on both sides to try to make it not be a conductor. And then we typically put cathodic protection on it too. This is one thing that the utilities usually don't do, but they should do, because a lot of times utilities get paid to do this as part of the transit system. They need to do an integrity evaluation of the pipeline. If that remaining life of that pipeline is less than the remaining life of the transit system, it should be replaced. Whether it's, you know, needing to be relocated from a transit standpoint or not. Okay. We kind of said that. We're going to make it electrically continuous. We'll add cathodic protections to it. Pressurized pipelines, we always do that. Gravity pipelines, it kind of depends. If it's a 66-inch diameter ductile iron storm sewer that's right next to the pipeline, we're going to take care of it. I mean, it's a pretty good conductor, even though it's not pressurized. But some other things, it kind of depends. This is kind of what it looks like. This one doesn't show a casing. There should be a casing right here, but that's kind of what it looks like. This would be an insulator here. That would be an insulator there, and then we put testations and cathodic protection on it. That's kind of what it looks like on a drawing, although you very rarely see 90-degree bends there. this, hopefully you guys can see these better than I can. There's a glare up here, but this is what the joint bonding looks like. This is a ductile iron pipe bond, or joint. We put bond wires across it. So it's electrically continuous, then they put this is a shrink wrap coating around it. That prevents those holes in there that you saw in one of those earlier slides. If all else fails and the pipeline gets too much stray current on it and we can't engineer it away, we put in these mitigation bonds. That's the last resort. There's the only place you really see these are like on really older systems, like up in Philadelphia and Chicago and some other places. There's a bond in Philadelphia, I used to live up that way, that would have a 600 amp current flowing through it. 600 amps flowing through a utility bond. That's the gas lines and the water lines and stuff all collecting stray current and dumping it back to the transit system. That bond breaks. You saw what 1 amp will do. 2 days it'll put a hole in a pipe. You got 600 amps. Granted, it's over several different utilities, but it can be a real problem real fast. They continuously monitor those bonds. The utilities take turns monitoring it. But as soon as you put a bond in, you lower your resistance to ground because you're tying other stuff into it. So it increases your stray current, and it's a domino effect. So we really don't do that. We try not to. And we always put a reverse current switch in it because you want it just the current go where you want it. You don't want to push it back this way and discharging because the current, you saw that voltage, it goes all around. So the current would be going like this if you didn't put a reverse current switch in. You want it going where again, it's managing the current. But again, we try to avoid that if we can. Okay, that's just kind of saying that. It blocks it one way. It's a diode. It's a fancy diode. Okay, now we built the thing. What do we do with it? We always test it out. A new system should always have these tests done on a baseline stray current survey. All right, we go out and we survey all the existing utilities before we turn on the traction power. Before we energize it up, we go out and do a survey of the utilities around it. That serves two purposes. The most important purpose it serves is it protects the transit agency from claims against you caused all this stray current. If there was already stray currents there, this is really better for extensions and stuff like that. But if there was always some stray currents there, you got to say what was here before you turned it on. Then this pre-revenue survey, that's when they're doing the train test and they're testing everything else before people can ride on it. That's the best time for us to test for stray currents because we can take a test train and start at one end and run it to the other end and do all our recordings and tests and see how that one train affects it. You saw how the graph was simple when one train was going down the track. So when it's a simple graph, it's a lot simpler to troubleshoot. Okay? And then once they get ready to put all the passengers on, you got to do it again because now it's on full load. And then that's the thing you do. That's where you set your trending right there. And you identify, is there anything that's got so much stray current we got to do extra work to mitigate it to make things safe. And then that's what you used as your baseline going forward, that this is what it looked like when it was brand new, and is it getting bad? Do we need to do some maintenance or not? So what do? We monitor that track to ground voltage like we saw earlier. We go out and test the track to ground resistance. We said like 500 ohms per 1,000 feet. We go out and do a test on that. We test the contact rail or the OCS. We can do that test, what the resistance earth is there. All that bonded rebar we got, we can use that to see how much current's actually flowing on those rebars to see how much leakage we have. That's part of that baseline survey. We look for increases in that or decreases in that, and it can actually help us to troubleshoot where it's coming from because we see how the current's flowing on the structure. If we get a big spike in a current, we know that's where our leakage area is. And then any cathodic protection we put in, we got to monitor that. That's what monitoring track to ground voltage looks like. This is what they call a negative return board in a traction power substation. These are all cables going out to the tracks that bring in the current back to the rectifier. We hook on the bus bar there. We got a recorder here, and we can have a connection to ground. That's our voltage to ground. And like you saw before, that's what the graph looks like. That's one of the things we monitor. What we look for is there any big spikes in this, or does it go flat line on us? Because what you see here, that's what they call non-revenue. That's when there's no train running. In MARTA, it's 2 to 4. Some other places, it's 12 till 3. Some places are 2 to 5. But that's when they're not running any trains. And that's a very important little piece right there for doing analysis, especially on pipelines. because you look at how the pipeline's responding there versus whenever there's a lot of activity on the line. This is not a great picture, but this is how we test our track earth resistance. It's really a simple test. All we do is apply a current and look for a voltage shift. It's measuring a resistor, E equals IR. And then we normalize it to how many track feet we have here, and then we have a criteria for, like Ballast Track, it's common to be like 500 ohms per 1,000 track feet. So we normalize it to 500 track feet, or 1,000 track feet, and we can tell whether or not we have sufficient resistance. Same kind of thing for a contact rail. In this case, you can do this either in the traction power substation or you can do it out on the tracks. We de-energize this to do the test. That's 750 to 900 volts. You were talking about that being safe earlier. You don't want to touch that contact rail because that's 750 to 900 volts to ground. This rail right here, if there's train activity on it, that's the 50 to 70 volts per ground. Okay? And we've got a connection to ground. This light post is grounded, so they're measuring the resistance to ground. They're using a mega ohm meter for that. There's a lot of different ways this thing can get low resistance. These are some things that I chase on transit systems that I do testing on for maintenance. Switch machines. We saw one of those earlier. There's a lot of different moving parts that are insulated. There's just a whole range of things that we have to look for. And here's what it can kind of look like. Ta-da! So that's stray current. If you have a bad joint here, you're going to have current jumping off here. If you have a bad impedance bond, you can get it on your pipeline. Yeah. This is some of these last slides are some of the things that you see on an aged system. This is what they call a high rail access system. You saw that on the other. Basically, it's wooden panels or sometimes rubber panels to where they can get on the trucks that have the rubber tire trucks, but they got what they call high rail. They got rails on them that they can lower down hydraulically to drive up and down the tracks. This is how they get on the tracks. They got panels there to make it, so they do that. This is what they call a tail track. It's basically a storage track at the end. This one actually is at the end of this right here. You can see doesn't have the inch clearance. It's got weeds growing over it. And that's not low resistance to ground, especially when it rains. There's that switch again. Any one of those insulators can go bad. This is tie and ballast track. If you look right here, I don't know if you can see that well or not. There's supposed to be little insulated white nose pieces on those fasteners there. They're all busted up and gone. So what that does, that takes that rail, ties it into this tie here, because that's a cast iron, what they call a collar, that's embedded in this reinforced concrete tie. So it basically makes it a pretty good ground. And this was a funny one. This is something that we had a hard time finding actually. This is where they put what they call a flag on the track for safety. Lets trains know there's not anybody there. They forgot and left one on there. And you can see right here where it's eating away this. It's eating a hole in here, and it's getting right here. And it was intermittent. It depended on if there's train go by one time, it'd not touch. Train go up by again, it would touch. And that track earth voltage that you saw, there's like 50 volts, it would go down to like 10 volts. And then it'd come back to 50 volts. Then go back to 10 volts. Then come back to 50 volts. And you have to be there when it's low to find it. Although we found this one as much visually as we did anything else, and it was interesting. Here's a problem we fixed. This is what they call a rail lubricator. It's to make the rails not make noise. Mostly, it's rail squeal. It pumps grease out onto the wheels. Well, you can see it kind of builds up. And grease in itself is not really all that conductive, unless they use a lot of additives in the grease, and then it can be more conductive. You get dust and dirt and bugs and other stuff in there, and rail. There's iron that comes off the wheels from rail wear. And that turns into a pretty good stray current area. Well, I put some geo fabric there. You can actually clean it every once in a while, so it makes it maintainable. And this next one, you're going to see why I don't like that pretty green grass track. This is what it looks like whenever it gets older. Okay, this is New Orleans. Okay, That's been in the ground for a while. That at one time had some rubber boots around it, but you can see that that's low resistance track. Okay. Last but not least, anybody got any questions other than wanting to go watch the football game? It used to be called National Association of Corrosion Engineers. It's basically it's like IEEE for corrosion engineers, or ASCE. You know, it's our industry organization. There's a neighborhood of 25,000 members worldwide. We have an annual convention that draws in 5,000 to 6,000 member range. It's manage how much current's going through there. But bonds are a maintenance nightmare. And a bond will also lower the resistance to ground of the track system, so we try to avoid them if we can. I've never installed one. I've had to test them, but I've never installed one.
I was kind of surprised when you started off. You never asked about chemical engineers. Didn't ask it seemed like that'd be an accident.
I'm a chemical engineer. I got my degree in chemical engineering. Yes?
No, I was just kidding.
Oh, okay. Well, it's an electrochemical reaction, so it's... Any other questions? Thank you for your time. I appreciate it.
As a token of appreciation,
Fantastic. Thank you. The one I've got, I dented it. I've got one somewhat like this that goes to work with me every day. I dropped it on the concrete. Thank you.
We hope you enjoyed this recorded presentation given at one of the Atlanta Metro Chapter meetings of the Georgia Society of Professional Engineers, an affiliate of the National Society of Professional Engineers. To find out more about us or to join us, check us out at gspe.org.